So after 8 minutes, it's pretty darn close to room temperature. Use your model to predict when the temperature of the coffee will reach room temperature to 3 significant figures. So this is a weird wording because this it looks like it reads like we want the answer to be in 3 significant figures because that's normally what we're talking about here. But this is actually asking something completely different. So this is where sometimes these application problems just really get the best of us. So will it ever reach room temperature if we look at the model that we created? If we look at the model that we created, we've created one such that we have a horizontal asymptote at our room temperature. So it's 75 times e to the negative 0.23995x plus 20. I'm going to set my window. We're talking about 8 minutes, so 10 there. Let's do 15 just in case. We don't really care about this. We know our initial temperature is going to be 75, so let's go up to 80. Oh, sorry, not 75, 95. So let's go up to 100. Okay, so we can see that it tapers off at 20. And if we go and trace or do like menu, yeah, we can trace that we're like, okay, when is it getting close to 20? When is it going to be equal to 20? And hopefully by this point, you're going to start thinking to yourself, it'll never be equal to 20 because it's the horizontal asymptote. It's the whole point of what we made this to be was for when it'll be tapering off, never reaching 20. But you can see that at some point, our calculator is giving us an answer of 20. And it's because our calculator is giving us answers to 3 significant figures. And so to 3 significant figures, at some point, we do reach 20. We get to a point where the value that we get is so close to 20 that when we round it to 3 significant figures, it is essentially 20. It's approximated to 20. So that's what it's asking here is, when will the rounding of this number become essentially room temperature to 3 significant figures? Well, a number that would round to 20, 3 significant figures wise, try and think about numbers that wouldn't work. 20.9 wouldn't work, right? 20.8 wouldn't work. 20.7, 20.6, 20.5, all of those would not work because they would round up to 21 to 3 sig figs. Well, yeah, and technically what I'm saying here is 0, 9, 0, 8, 0, 7, 0, 6, 0, 5. Sorry, I made a mistake. So this is a good way to double check and see like, okay, when I make mistakes, I realize, wait, that would round to 2 sig figs 20, but I'm talking about 3 sig figs 20. So that means I need to actually look at the next decimal over. So it's 20.09. That would round up to 20.1, which is not room temperature. That would round up to 20.1, which is not room temperature, right? All of these would round up to 20.1. Okay, anything lower than this, 20.049999999999 would round to 20.0 as our 3 sig figs. So we want to know, when will our model be at this value, essentially, or anything less than this? Trying to think of a way to say that so it makes a little bit more sense. We want to know, when will the temperature get to a point where it's below, almost immediately below 20.05? And so what that means mathematically is I set this equation to be, when will this be less than, strictly, 20.05? And we can think about it algebraically, right? We can also think about it graphically, visually. We always should be diversifying our perspective on these guys. that at some point, I'm going to make it really dramatic here, but it won't be quite as dramatic on the page. At some point, the graph, the temperature will decrease such that it's below 20.05, but still tapering off at 20.0. And we want to know, when will it go below 20.05? We want to know, what is that time? So we could graph this relationship. I can see it happening somewhere over here, that my 3 sig figs of my calculator are telling me to be about 20. So I might just leave my zoom in this. Oh, my Zoom is trying to figure it out. I'm going to leave my window like this and hit tab and just graph 20.05 and see, okay, it looks like they're right on top of each other. So I'm going to change my window so my X values are a little bit more to the left. So maybe I'll do 5. And now I can see, that point was there before. I hope we remember, but I didn't point it out, and I should have. Okay, so this and this are the equations. So now I just want to find the intersection. So I'm going to give myself a really large bound, and I can see, okay, at 30.5 is when it goes and intersects at this value right here. So the answer to this is anytime t, I guess it says x. Weird. Normally it's t. Is greater than 30.5 is what the calculator tells me. So anytime past 30.5 minutes, that temperature is going to be so darn close to 20 that it's essentially 20. This is a crazy complicated problem. I've never seen a problem like this on the IB problem, C at least, sorry. This is not something I've seen on an IB test. This is a textbook question that I think is a little bit difficult to understand and maybe not really well worded because of that 3 sig figs of like how the misunderstanding would happen. Your IB exams would be much better worded, although there's always an opportunity or always a possibility that you might not understand right away. Okay. Let's go to the next problem. Suppose that the population of zombie IB students is increasing at 7% per month. The population in September of 2019 is recorded to be 240 individuals. Assume that this rate of growth remains constant. Okay, so we're going to develop a model. So we have models for exponential equations. And we know that this is like our skeleton model for an exponential equation. This is for really complicated exponential models. Typically, if we're going to use this way of using an exponential model, like we did with our last problem, they will tell us. They will say, hey, there is all of these variables going on. If they don't, if they just leave it like super blank, we actually just ignore the r and we do y equals k a to the x plus c. So let me rephrase that. This model is the fully correct skeleton model, but it's really complicated and sometimes not exactly what the IB wants you to do in terms of a blank model. So sometimes we use this model instead. If they haven't specified that you should be using this with the R up here, just don't include the R because it makes it a little bit more complicated. So this is the skeleton model we're going to use to try and figure out what is the exponential increase, the exponential growth of these zombie students. We have 1, 2, 3 unknowns, which means we need 3 separate pieces of information. Maybe we'll make a system of equations. Maybe we won't. Maybe we'll just be able to find it in context. So we have 3 unknowns, and we need to have 3 separate pieces of information. We are given a 7% increase. Okay, that seems important. The population in September of 2019 is recorded to be this. Assume that this rate of growth remains constant. So if it's a growth, think about it for a minute. If it's a growth, that means it's going to look something like this, which means I'm going to have a horizontal asymptote that goes like this for my C, right? And so then I have to think about, in the context of this problem, what would be my horizontal asymptote? Excuse me. As it decreases, what will it never go below? And hopefully now we can see that it'll never go below, take a guess. As we move to the left, it'll never go below 0. I haven't graphed it like that in this problem, but that's okay. That's not the whole purpose. The purpose is to kind of understand, what would this be approaching? I would never have less than 0 students. I would never even start with 0, right? It always starts with at least 1. So it's infinitely approaching 0 to the left-hand side, but we know with growth, we don't really care about that because it's actually just growing and going and going and going. There's no stopping this growth. So it actually means that C is equal to 0. Oh, awesome. Okay, so there's not even a C. So now it's just y equals k(a) to the x. Okay, so now I can start thinking about these pieces of information. If 240 is my initial value, then k plus c, or 0 in this case, would be my initial value. So 240 is k. Then A is my base, the amount in which I'm growing. And it says we're increasing at 7% per month. So if we're increasing by that much, that's 100 plus 7%, so 107%. In decimal form, that means we put the decimal right here. So that is our exponential model, and not super complicated to create, but we had to know a few things. Like, we had to be able to spot that our horizontal asymptote is C, and we had to know that R doesn't come into consideration unless it tells us to put R into consideration. Okay, now we're going to use our model to predict the number of IB students in April of 2020. It says it's increasing at 7% per month. So our input is months, and our output is going to be zombie students. So in April of 2020, that is not a full year later. So September to October, November, December, January, February, March, April. But this is 0. Yeah, no, that's right. 7. Okay. Whew. 7 months later. So we go ahead and plug in 7 up there, and we get 385.39, And if it says the number of zombie students, we have to realize, even though they're zombies, we could maybe potentially have half of a zombie person. We will say 385 students.